discussing the events from the week of the 26th of February to the 1st of March. This is also a three-part series because there just were a couple of events and I want to split it up. And what I want to do is actually in part one, I also want to make this part of the foundation models for embodied decision-making agents, part 7. Sorry for all the parts, but so this is part 1 of the events discussion and simultaneously part 7 of the series of foundation models for embodied decision-making agents. The reason that is the case is because we had the opportunity to attend 2 lectures, one by Quan Vong from DeepMind, the other by Dorsa Sadigh from Stanford, and they're both in the same realm. They talk about, in a nutshell, what both of them are trying to do is create an internet of data and a base to create a transformer-based approach towards robotics. So what that means is you have this success with large language models, for example, ChatGPT, or what Anthropic's doing, or Perplexity, and Grok, and things along those lines. And what they were able to do is take a large body of data from the internet or from X or from both, and train a model based on self-attention architecture, and then have it generalize across really all kinds of textual modalities. In other words, we can write programs, we can do math, we can do semantic stuff, like we can ask the model, if I'm on top of a mountain and I want to go down that mountain, how do I do that? Things along those lines. So what's really key now on the robotics side of things is people are trying to replicate that same idea. So one is, okay, can we even have a transformer-based architecture, which boils down to the question, let's assume we have data. Can we tokenize that data and then train through, let's say, variational inference and mask autoencoders? I'm going to talk about variational inference also in this part, which is not directly related, but it is kind of really important if you think about it. David Bly, who is a professor now at Columbia, he gave a presentation at Stanford, and it just dawned to me, I mean, this is really the key. I mean, statistics in his form, the way he does it, is absolutely the key towards the question of how can we, so we have a bunch of data, and now we want to use transformer-based architecture to train that data and generalize. So the way we do it is, we have, in statistics terms, we have a very diverse set of data sources, and we kind of create a gigantic matrix of distributions where we say this type of stuff belongs, let's use the text domain as an example. So words like I love you, I am walking on the beach, I am happy holding hands with you. These words all belong to a distribution. Let's call it happy, love, relationship, like things like that fit, or these words belong to that distribution. So then when we prompt tomorrow, when we prompt in inference time the model, and I say, I am happy walking on the probability that the next word is beach is very high, because all these words kind of belong to the distribution where also beach is part of, versus, let's say, I wouldn't say I am happy walking in the dark cellar of a haunted castle. Like, that's not something I would predict, because it's just very rare that the data set has seen these types of things. So in that same context, we could think of using variational inference and its follow-up research, the follow-up models and research which is going on still in statistics, use all these models to tackle robotics in a similar way, like the text people around OpenAI and now all these other model developers, how they're taking advantage of text. So this is the key idea, and we will talk about Quan Vong, who will talk about robot scaling, the journey from RT1 to RTX at DeepMind, and how to unify data. So he talks a little bit also about just the nitty-gritty of engineering. Dorsa is a researcher, interesting lady, I think, just interesting to listen to, direct, clear, aggressive. I like that. And then David Bly, that's the third conversation in this part 1 of the events discussion, again, part 7 of the Foundation Models for Embodied Decision Making series. David Bly we're going to talk about variational inference and the actual underlying statistics that fuel all these models. So let's start with Quan. So he's at DeepMind, and he gives a talk here at Stanford. There's also an online talk available from a talk he gave in Vietnam, actually, in the sort of the Vin AI context. They give talks. Vin is the company, I believe, they do VinFast, so it's sort of a conglomerate that does high-tech stuff in Vietnam. Anyway, so he gave this talk, and I think the reason he's going around talking to people is because what DeepMind's trying to do is create a unified data set around the world, sort of bootstrapping an internet of data for robotics, which is great. I think it's a fantastic endeavor. So he gives a talk and sort of gives the history, how RT1 came along, RT2, and now RTX. What are the differences? I don't think it matters that much because I quite frankly don't understand fundamentally what the differences are. I believe the fundamental idea is that it starts with a paper called SEIKAN that we discussed here, which is use language to give instructions to robots. And then it goes to RT1, sort of, okay, how do we turn language into low-level action, right? How do we turn, hey, go grab this Coke bottle into actuators, into real actions? And then the whole idea is, and this is sort of where RT2 and RTX come into play. And now, can we create a massive data set? And if so, well, what kind of data do we even use, right? I mean, think about it. Like, imagine we have 100,000 labs in the world collecting data, and they're putting it somewhere, and this is what's going on today, right? We have this, if you think about it, we have this bespoke alchemy style research in the cellars of research institutions, similar to chemistry in the 17th and first part of the 18th, and first part of the 19th century. So before the periodic table comes along, and a lot of things have to happen. I mean, even today, if you think about the chemistry, and similarly physics, but chemistry is a good example. The problem with chemistry in the 19th century is we don't even know how to talk about things, right? What did the periodic table do? It created a unified data structure. So this thing that we call hydrogen atom encompasses a lot of things. I mean, quantum physics can tell you a lot about the hydrogen atom. And if we don't have a name for that, and if we don't have a sort of high-level abstract description, i.e. one proton, one electron, I believe one neutron, I'm not sure, it doesn't matter, or two neutrons, and then we have these different versions of hydrogen. But if we don't have this high-level abstract description, what are we describing? Are we describing the energy levels of hydrogen electrons that can have different manifestations? You see, I mean, this is unbelievably complex. So what we need is a high-level unified language for hydrogen, lithium, helium, and so on and so forth, until today we have 200 plus elements. And so once we have that, we can start talking about the same thing across the world, and we can also unify our experiments. So when we do a hydrogen experiment, this is how we do it. These are the instruments we use, and these are the results, so we can evaluate them. So very similarly, the people at DeepMind, that's what they're trying to do with robot data. So and there's other people that are interested in this, of course, but I'm just using now Quan's presentation, and kudos to DeepMind for doing that. I just want to also acknowledge all the other people. So that's what they're really trying to do fundamentally. Now, what they're also trying to do is bring in other modalities, in particular vision language action models. That's RT2. So RT1 is, let's call it just text, and then low-level actuators. RT2 has vision language action. So take vision, fine-tune on text, and then output action. I think intuitively that makes a lot of sense, right? You have, let's say, you have a robot that is picking up a Coke can. You can fine tune on text. Well, don't hit the person that is standing next to you. Bend, but when you bend, make sure when you stand up not to hit something. I mean, you can fine tune. You can give the robot textual instructions that could be very useful, and that's sort of the world that RT2 lives in. RTX tackles the data scarcity in robotics. Lots of data sets are available, but they're isolated, they're in silos, and they're not publicly available. So these are the problems that they're trying to solve. And then they have a couple of ideas, the Q transformer. So now we're going into the realm of how can we use transformer technology for robotics? And I think this is, to me, this is really where the rubber meets the road. Because we can talk about data as much as we want. I think what we need is overlying architecture, a certain goal that we're all working towards, that I think will bring us further. And I think building a data set that then can be used for masked autoencoder training. In other words, a pre-trained model on which we can build. I think this is what Sergey talks about in one of his keynotes, when he talks about how about we start with a robot fleet and then build on top of it. This is what Figure CEO talks about. And this is certainly what Musk thinks. Maybe he doesn't talk too much about humanoid robot right now, but that's the idea. What's the powerful idea behind having humanoid robots working in a Tesla factory? Well, yeah, it saves a couple of bucks on human labor. Maybe it's a little safer. But what it does, it creates a data set that maybe if we're smart about it, we can use to build a transformer-based architecture that then can be used for generalized robots and generalized robot actions. This is obviously what's happening right now in the self-driving space. And I haven't heard much about out of Tesla nor Waymo, how they're thinking about this. But I believe that this is certainly a possibility, that maybe the models could be rewritten or the approaches could be completely rewritten as sort of pre-train and then few shot learning and or fine-tuning and then inference. I don't know about how far this can go. These are certainly big questions, trillion-dollar questions that probably I wouldn't even be able to, like if I was at a Tesla AI day, what would I ask? I would ask, there is this successful approach in the textual space, which is we use a bunch of text, we train it through the self-attention idea, which is really trying to attach distributions to words and combinations of words and words that are in certain positions to each other. And then at inference time, we try to sort of guess which distribution the prompt belongs to and then predict the next word, which is kind of what David Bly in his variational inference talk talked about. Now, can we use the same idea for robots? And can we, instead of text, have what kind of tokenization will we even use? Like, what are the ideas here? So this would be the question. And with this, let me go to the next presentation. It's Dorsa Sadigh. Now, she has given a presentation at Stanford last week. She also gave one at MIT recently, and she gave one at Berkeley. So I'm going to just combine, because it's very similar. What's her idea, right? What she's mostly working on, at least given the presentations that she's giving, I can infer that she's trying to understand two things. One is like, in order for us to learn something, we need to first represent data in some sort of way and then learn from there. Well, probably in some sort of offline setting. But so what kind of representation do we even use? And then I think as a conclusion, she goes towards the idea of a foundation model, which is absolutely prevalent in the MIT lecture, where she actually talks very specifically about the foundation model. Now, let me go through some of the stuff that she talks about, and then end with the foundation, because this is really the key, right? It's the foundation model. And the idea of the foundation model is that you have a large amount of data, which is trained maybe through some sort of masked autoencoder or something very similar to what we have in the self-attention architecture on the large language model side. And from there, we can then learn more specific tasks. So we can use a transformer to to represent the knowledge that is required to then fine-tune the task. In the lecture, she starts with data representations from human feedback. So she starts very basic. If a robot wants to learn how to pick up a jar of orange juice, well, it can just watch humans do that. Or it can do it and then be corrected by humans, or it can be teleoperated. So there's a couple of things that she talks about. I think what's interesting is actually her work that she's done with Erdem in a paper. Erdem, his last name eludes me right now. The question here is, what kind of questions should we even ask? Or if a robot is guided by questions, so meaning the robot actually asks me, okay, if you want me to pick up that jar of orange juice, should I go left or right? Should I now go with this force or that force? So in general, this is a way to solve the problem. This would be, I would say, like a DeepMind approach, where you're actually delegating tasks using maybe some sort of large language model, and you're delegating tasks by asking questions and getting feedback. You can get that feedback, by the way, also from a large language model. So this could be a sort of an end-to-end, all-in, automated way of dealing with the problem. So you could have a large language model answering questions, and the robot is guided by the answers of the large language models. But Erdem's work is really in the realm of, okay, what kind of questions do we even ask? How do we get the most information efficient questions that most efficiently subdivide the search space into where we want to be? So I thought that was pretty interesting. But now let me get to the sort of gist of Dorsa's talk, and that is really the transformer side of things. So we have image and text. We can train that on a large amount of data in some sort of transformer type architecture, and then use that to fine-tune. I think this is the dream. We're not there yet, but this is the dream. And I think another very important sub idea or sub path in this context is the idea of having a large robot fleet out there and then learning from that. And I think that would be my main question to Dorsa in the next lecture that I'm hopefully attending. Like, how do you feel about the idea that we have Figure, we have Tesla, and a couple of other companies that are deploying autonomous agents, so robots that are maybe, or even the robots that other robots like KUKA and these types of robots. How about we start collecting all that data, be unified in a certain unified data format, a little bit like the internet with text, and then we build a large language model, sort of a transformer-based model, a masked autoencoder, or something along those lines, to then train that fleet of robots, create a pre-trained transformer, and then have fine-tuned training based on that representation of knowledge for more specific tasks. So if we have robots that are able to pick up stuff and put them in certain bins, maybe from there we can fine tune and then have the robots pick up stuff, put them in bins, and put maybe softer things on top of harder things, and stuff like that, and then learn from there and sort of bootstrap. Like this is what Sergey was talking about in one of his keynotes. So to summarize Dorsa's talk, I think what I find really most interesting about her approach is first the representation. So how do we represent knowledge in a unified data format so we can actually learn from there for robots, and then also the idea of the foundation model. The last presentation I want to talk about in this particular episode is David Bly's presentation he gave at Stanford last week, and it's about variational inference. Now, variational inference is a statistical method that he co-developed with other people, and the idea of variational inference is that you are trying to do the following. You have you're given a certain data point, and you're trying to guess which distribution that data point belongs to. And the way you do that is through optimization. So you kind of iteratively try to figure out where it belongs to. And that's really the fundamental idea behind, let's say, transformer technology today. If you think about what transformer technology does, let's say if you take a large language model like GPT, it trains on massive amounts of data. And what it does, it kind of creates a gigantic matrix of distributions where you can say that, look, and it really does that, because if you take self-attention and the positioning of the words and things like that, which are key in the self-attention architecture, if you take that at heart, then you realize that what's been done here is we have a massive amount of a huge matrix, right? That says, look, the words "I love to walk on the beach," they belong together in a context of happiness. Now, beach belongs to "I love to walk," but then also, cadavers often are found on the beach because they die and then get swept onto the shore. Obviously, beach has a different context there than in this. So depending on the context, the word beach belongs to the distribution of maybe something negative versus something positive, something happy, something more serious, something you have to pay attention to. The beach is gray and the hurricane is nearing. That in this context, the beach is actually dangerous. You should go away. Versus the beach is beautiful on a sunset and there's this beautiful woman waving at you. Maybe you should not walk away from that situation. So depending on the context, you have different distributions where now if you train a model through mask autoencoders, what you're doing is you're creating this massive, you're creating a gigantic matrix of distributions, or like Andrej Karpathy says, you're just compressing knowledge about stuff that is available on the internet. Now, once you have that, you can now prompt the model. You can say, I walk on the beach, and I am, and then predict the next word. Now, you could say I'm happy, or I'm in danger, or I'm whatever. That depends, and that goes back to Dorsa's question also, like how much informational content do I have in the prompt, for example? Like, how do I prompt intelligently? This goes into prompt engineering and all the stuff that also Andrew Ng's talking about, because what you're really trying to do with prompt engineering is you're trying to find that you're trying to kind of get rid of all the distributions that are unnecessary. So I walk on the beach is not a very good prompt because it could have dangerous or beautiful or sad or happy kind of situations connected to it. Therefore, it's harder to predict. And why am I talking about all this? Because this is really the heart of variational inference. And now back to David Bly. The presentation was really interesting because it shows you a couple of things. It shows you what the statistics actually are that are underlying modern AI. So when we talk about generative AI in general, transformer technology, pre-trained models, all of that stuff, it all goes down to variational inference. Now that variational inference can be done in several ways, and this is active research, and there's what Stefano and Ron is doing, but score-based techniques. there are more efficient ways to guess where a certain data point, what distribution it belongs to. But in the end, the concepts are very similar. And Blay was talking about all these things. I personally am not very familiar with the mathematics and the subtleties of the actual models, so I don't want to talk too much about it here. And I'm also, quite frankly, not that interested. But I think one concept that is interesting is the KL divergence, which is really what you're trying to do is you're given a prompt and you start with a certain, you say, okay, how about this? You're given the word beautiful in the context of my girlfriend is, right? And now the word beautiful, and what you're trying to guess is, you're prompting my girlfriend is, and what you're trying to predict is the next word. And you're trying to sort of match the word that belongs to this particular distribution that my girlfriend is belongs to. And the way you're going to do that is through variational inference. And you're going to start with, let's say, you're going to put my girlfriend is, and you're going to have it in sort of a Gaussian distribution. You're going to say, okay, this belongs just to a random distribution. But then you're going to iteratively try to find the distribution that this belongs to, and it actually belongs to the realm of maybe either expressional words such as beautiful, ugly, nervous, things like that, or tall or short, like that. And you start narrowing down the distribution until you find the most likely distribution that this prompt belongs to, and then you can from there predict the next word, which could be beautiful, or it could be short, or it could be tall, or it could be smart, or depending on, again, if your prompt is just my girlfriend is, that's not a very good prompt because you have a lot more entropy in this prompt. But my girlfriend is blank, and that makes me happy because she is so good looking that I almost faint every time I see her. So if I do that, then the entropy gets much more reduced, and beautiful is probably the right word to choose. So in KL divergence, what we're trying to do is we're trying to sort of match the distribution that a certain X observable belongs to. And we start with maybe a random distribution, and we narrow it down to the distribution that it actually belongs to based on the training data that we have. So I thought that the talk then, Bly's talk goes a little more. It goes to stochastic variational inference, which is just a way to deal with very large data sets, and stochasticity allows for reduction of the search space. Think of it like that. If you're in the Amazon jungle and you want to find your way from A to B, you can try every possible trail, or maybe stochastically you can just randomly choose a couple of trails, and you will probably have a similar success rate, but you will waste a lot less energy than if you try every single one. I think that's kind of the way I understand this. There's also black box in variational inference, which sort of allows you to do a little bit more general search through the potential distribution space. I wasn't 100% clear about that. There's a couple of presentations that, a couple of papers that he introduced here. But I think for me, most importantly here is really the idea of variational inference as the core underlying modern machine learning, as the core underlying generally statistical methods in trying to match massive amounts of data towards a certain input that then can be, again, matched to a distribution that is found in that massive amount of data. I think lastly, what I want to say is, again, when we talk about what transformers really are, it is sort of a sorting of large amounts of information into a matrix of distributions, and then we can use prompts to match those prompts to those distributions. To summarize, 3 presentations that are all part of the foundation models for embodied decision-making series. One presentation is Dorsa Sadigh. She talks about knowledge representation, in particular, foundation models for robotics. We have David Blay talking about variational inference, which is the statistical methods underlying all modern architectures in generative AI and things along those lines. And lastly, we have Quan Vong from DeepMind. He talks about the world before foundation models and after, and applied to robotics. This is very similar to Dorsa's talk, where I think in general both of these endeavors are leading towards the creation of an architecture for foundation models for robotics, which is exactly what we're working on. Thank you.